Welcome back to this presentation. My name is David and I'm a structural engineer. This is a continuation of the previous presentation that we did on the design of aircraft hangars in full compliance with Eurocode 1 and 2. So today we shall be looking at how we proceed with the design of this and also analysis of this structure. And let's get started. So the first thing that you should do before you proceed is to add the roof panels and the wall panels. To do that, you should come here to model, and then you go to roof panel, and then you snap from this part, this point to this point here. Then you proceed to this point. Then you proceed to this point here. Then you proceed to this point. So you have your first roof panel added successfully. So the next thing is to do another roof panel on this other side here. So just come and add that. This other side, do the same. Same. Then you snap that point and you have your second roof panel added successfully. It's always good to keep validating your model. So just validate here. We validate to see if there is any crashing of the members in our model, and we can see we don't have any validation issues to do with the modeling, and these are just validation issues to do with the loading because we are yet to add the loads to our structure. So let's proceed with the modeling of the wall panels now. So just come here, and now you just come here to this point, snap to this point, and then you proceed. You can just snap to this other point, then proceed on the other side. You snap from this point and then snap to this other side here, like that. Then you come here, you can turn off this because this is going to be irregular shape. So just come here, snap from this point, snap to this other point up here, then you snap to the peak or the apex of this, then to this other point here, then to this other point here, then to this other point, and then proceed to this other to the far end here. Just snap from this point, snap to this other point here, the same to this other point, then you snap to the bottom point here, and then to this far end here, and then to the origin, and you have your wall panels added successfully like that. So just validate your model to see if there's any issues to do with the crashing. You can just see you have this one here. What you need to do, just delete, and you just redo it. So just come here, snap, come here, snap to this point. Make sure you can see the point clearly. Snap that point, then to the apex, like that. Then validate. You can see we don't have any errors, so that's how you resolve it. So let's just proceed. After this, what you should just come here to loads, load cases. You can see we have defined our loads here, and for this one you should always select the dead load here, select the roof imposed, then just click OK. After this, you are supposed to define the load cases for the width load. So just come here to width wizard, and then you can see these options for the data source. This one is for the UK, this is for Irish. Here we have the worst case data, And down here we have data for each direction, so we just go by this because we are not in UK or Irish. So just select this, then just go to next. And here we can see we have the options for various conditions, like when we have to consider the orography. We have a case we have to consider the tall building structures, consider obstruction, and for our case we are just going to leave it like this. So just go to next, and then we have our fundamental basic width velocity. We are going to go by 25. It's always good to refer to your meteorological data from the place where you come from, so that you can have the correct information to input in the software. So just go to next, and then you go to next, then go to next, and then you can just finish. And now after this, what you're supposed to do, you can just come here to decomposition, so that you can have your load decomposed into your structure. So just click like that, and then just come here to with load, then go to with load cases, then you just auto generate here, because the software is just going to auto generate the load cases for you automatically. So just click OK. And then after this, if you want to see how the wheel loads have been added to your structure in all direction, just come here to this wheel wizard. Then you can see the wheel loads in this direction. Just come here, you can choose this different categories, and you can see this is now in the 0 direction. On in the 90 direction, you can see how it looks like. You can just see it. And also if you proceed here, you can see the CPE in the negative direction, and you can also see here for 180, you can see all this. And for the net pressure, you can also see how it looks like. So you can always get to see this, and if you wish to update, you can just update. So this is how it looks like. Remember, the weight loads are one of the critical lateral forces that you should consider when you are doing your structure, because especially for the roof, where you are to consider the uplift pressure as a result of the wind. So it's important to consider that. Then after this, what you're supposed to do, just go here to load. All right, can just now can go here to your loads here, to load cases, and you can see your load cases have been added here successfully. And then after this, you can proceed with defining your load combinations. And to do that, just come here and just generate. And we are going to consider the first two scenarios. This is for the equilibrium combinations, and this one is for geo combinations. And then here we select final, because we are designing the structure against collapsing, and we should design the structure to see how it behaves when subjected to extreme loads. And we can only do that by selecting final. If you select operating, it's to do with the serviceability limit state, and you're designing the structure when it will be in use. For the erection, it is when it is under construction. So just go to select final and go to next, and go to next. Next, the software is going to define all this for you. Then go to finish, then say OK. But before you say OK, you can define your envelope here. Just add the envelope, or you can just can just go by this and select the combinations that you want. So select the first one and the second one and these two for the wind, and you can just say okay. All right, so after this, what you're supposed to do, you can just come here to structure like that. And after this, what you're supposed to do, we are supposed now to add our loads to the structure. So just come here, come to dead load, or we can start with impose load. But before we add the impose loads to the structure, it's good to understand how we get to define these loads as per the Eurocode 1. So just come here. I have done all this for the sake of this presentation, so you can see various impose loads for various structures. We have offices, residential living, rooms, corridors, and all that. So here we have the roofs, and we are going to consider 0.5 because for our case we need a roof that needs to be accessed occasionally and just for maintenance only. So we are going to consider 0.5. As you can see here, you can see it. Let me just zoom it. You can see we have 0.5 here for the roofs. Again, for the dead load calculations, I've done it here. You can see the component here that I've considered. We have the metal sheet, 0.6 millimeters thick, corrugated steel. The density of steel is 7850. I have calculated this and it's coming to about 0.05. Then we have the purlins. We are using this kind of purlins, and we can see we have 0.3 kilonewton per meter squared. For insulation, we have this insulation, which is about 0.05 meter thick, and we have this dead load calculated as 0.001 kilonewton per meter squared. For the fixings and accessories, this one we consider this clause of Eurocode, as you can see here, and it's coming to about 0.05. And when you do the summation here, down here we can see we have a total of 0.4 kilonewton per meter squared. And here we have the Eurocode references that we are using. And you can see how we go about it as per Eurocode 1. So here we are going to consider 0.1 for 0.4 for the GK or the dead load per meter squared, and for the live load we are going to consider 0.5. So let's proceed. So just come here and then you select impose load, and then after this you just come here, select area, and then here you're going to go by 0.5 like that, and then just select the roof panel and also do the same here. And after this, just come here and select now the dead load, and then you're going to change this value to 0.4 like that, and then you're going to add to all this just the same way I've done for the impose loads. And you can see them here like that. And after this, what you're supposed to do, you can just decompose your load to the structure. And after this, what you're supposed to do, you can just come here to analysis and you run your analysis, because now you have added your loads to the structure. So just come here to analyze, and then after this just select the first order and linear, because this is recommended, especially when you have these low-rise structures where you are not consider plastic deformation or plastic analysis. But in case you have these high-rise structures where you have to do seismic analysis and all that, it's always good to go for second order linear analysis. So just come here to first order linear analysis. You can select load combinations of your choice. I'm going to select the first 4 and just click OK. And after this, you can view the results for your analysis. Just come here to results, and you can select the one that you want to see. But before that, it's always good to select the load combination that you want to see. You can just come here, select this one, and then you can select the axial force, for example, and you can see the axial forces for this structure, especially for the columns. You can see here we have an axial force of 90 kilonewtons for the external column. This external column here, we have this we have 41.8, and you can also view the shear major and also shear minor, moment major, and all this data is important when it comes to the design of connections. Again, you can see, you can also proceed to view the results for the moment major here. And as you can see, we have the moments at the midspans are quite high for the rafters at the midspan, and also the columns at the midspans, because they are receiving more forces due to structure continuity and also stiffness distribution, and also they have high tributary loads coming from either side, unlike these ones that are receiving just from this side. So you can always view all this, and you can place your cursor or your mouse at the top of this, and you see all this information: the shear major, the shear minor, the axial force, the moment major, moment minor, and all that, and also the axial force. And you can see how the moment are changing as you move from the far end to the center, or at the midspan of the structure, just like I've explained. And if you want to see the values, you can just come here and you can see them, can turn them off. And then it's also good for you to see the deflection. If you would like to see the deflection, just come here to deflection, and you can see deflection for the structure here. This is the deflection for various structural members in this structure. And if you want to animate this, you can just come right click and just say animate, and you can see how the structure is responding to various loads subjected to various structural members. And you wish to make it look bigger, you can see how it's behaving. So that's how it looks like. You can just view, and then you can close this. And after this, you can proceed with what we call the design. So just come here to design, then you select design steel gravity. You should not go with design steel static. You do this when you are doing the seismic analysis. So just click design steel gravity, and then you're going to see how various structural members are responding to the loading. We're going to see the ones that are failing and the ones that are passing the design. And as you can see here, we have our columns. Here we have the legend that is telling you, showing you how the structure is looks like. The ones that have passed are green in colors, you can see here, and you have these ones that are failed that are in red in color. You can also see all this. Then we should look at these ones that are failing, and then we also have this one that's telling us a warning. We have a warning. What you should understand is that that's not a structural issue. It's just that the software wants you to get some attention to that member. Let's just open this, and we get to see check member, and you can see here the column has passed all the checks. The shear major is okay, the shear minor is okay, the moment major is okay, the axial design condition is okay, the buckling lateral torsion is okay. Actually, it's not required in this case. We have buckling compression, it's okay. Everything is okay as per this status, as you can see. And if you look at this warning and then you place your cursor on the top of this and you look, the program is telling you, the program has assumed that both the top and bottom flanges are effectively restrained at the top of the column. Please verify this assumption. So the software is telling you that it has made an assumption that the top and the bottom flanges of this structural member of this column are restrained at the top and at the bottom. So we should check and see if that is the case. So what you do, just come here and you select this column, and then what you should do, just come here to releases, just come down here to where we have release. Then you can see the column is fixed at the top and again it's still fixed here at the bottom. So the assumption is okay, the software is correct. So that's not a structural issue and you should not be worried about that. So let's proceed with these members that are failing here. As you can see here, we have this column, these rafters, and our columns have passed well, and you can see here they are passing at a very low utilization ratio, and we can see we have used the minimum section, that is section 152, and again our bracings are okay. And we can see for the rafters here, we have these rafters passing at a utilization ratio of 82, which is a very nice utilization ratio. It's because they have low bending moments, because they are on the external part of the structure. And you can see here we have these sections that are failing here. Let's just see why they are failing. Just click on this, right click, and we just check the member. I'm going to see the reason for the failure. You can see they are failing by lateral torsional buckling and all these other failures to do with buckling compression, and all these failures also by deflection. And we're going to resolve this. So just say close this. And if your beam is failing by deflection, of course, what that means is that you should increase the depth of that beam so that you make it stiff along its depth, and in that case it's going to be able to withstand deflection. So let's just design one and we see the section size that is demanding. So just click this one, right click, then go to design member and go to design static. And then after this, you're going to see the software is going to do automatic design, and we can see the section size that is passing here is universal beam 305 by 165 by 40, and this is the section that is passing the design. So just close this, and after this, what you're supposed to do, you can just highlight the rest of these rafters like this, and you change the section size to 305. So just select all of them like that, one by one. It's very easy to do that. Just select all of this. So just select this, just press Ctrl and you continue selecting just like this. And after this, what you're supposed to do, just come here to section where we have all spans, and you select this section, you go by 305, and then you can see the section sizes have been updated successfully like this. And then what you're supposed to do, and then you can redesign your sections. So just come here to design, then you go to design steel gravity, and you can see the sections are being designed and the analysis is being run, and we're going to see the results for this in a few, and you get to see how it's responding. And as you can see here, we have still some members that are failing, and we can just design one of them and you see how it's going to respond. So just click one of these. We're going to right click, and then you go to design member, then go to static, and you can see it's demanding a bigger section, that is UB 356 by 171 by 45. So we can just select this, and now this, and also the same case for this one and this one. And then after this, you can just come here to the same position, and you just come here to sections where you have all spans. Go select a bigger section, 356. And after this, what you're supposed to do, just come here to design, and then you go to design steel gravity, and we're going to see that the sections are supposed to pass the design. And as you can see, our sections are passing very well for the design. And what you're supposed to do now is to proceed. Now, if you look at this, you can see we have our rafters designed, and also we have the steel columns here. I want to draw your attention to something we call releases, and you can just come here and analyze again. And just do the design, and we see how it's going to respond. Then we just come here to releases, and then I want to draw your attention to this. As you can see here, we have the linkage for the different categories of member releases, or the eight conditions for various members. Here we can see for the cantilever it's red in color, for the partially fixed is blue in color, and for the fixed is green in color, for the pinned is yellow in color. So I want to draw your attention to this one, the fixed end conditions. And you can see here for our rafters, all of them have got fixed ends. For the purlins, we have these pinned end conditions because we don't want our purlins to transfer movements to the columns. So when you have them pinned like this, the result is that we have zero movements being transferred to the columns. So now look at these rafters. You can see all the rafters here have a fixed end code. They have fixed end conditions. That's why they are green in color. And the reason why we do this is because when you are doing your design, it's always good to do a design that is economical and also eco-friendly. Now, what happens is that when you do your economical design, you should always refer to the first principles of economic design. And from the very first principle of economic design or economical design, we get to say that the deeper the section, the higher the cost of the section. So in this case, what makes the section to be deep is when the span is long, because in that case, it is likely to fail through deflection and bending, and you can only resolve that by increasing the section size. So that tells you that you should always give priority to the longer spans. And in this case, if you look at this rafter here, it is about 10 meters. But again, if you look at this column here, it is about 6 meters. And you look at this, it's 10.1 meters. And it goes without saying that in this case, for the portal frame structures, it is always important to give priority to the rafters, because when you have your rafters fixed
on both ends, what happens is that there is the sharing of moments. There's the transfer of moments to the columns. And so in that case, when you have your moments transferred to the columns, we are going to have less moments at the midspan. You get what I mean? So that's to tell you that your beam is less likely to fail through deflection because you have already resolved that by distributing the moments to the supports. And that is a very perfect way to economize your design because you're going to use smaller sections and less deeper sections. And when you do this, what is going to happen is that the cost of the design is going to be low. On the other hand, if it happens that you use uh, pinned head conditions, what happens is that you have very big sagging moments at the midspan of the rafters here. And what happens is that when you have these big sagging moments, if you can just run the analysis here and get to see them, what happens is that when you have these big sagging moments at the end here, if the in this case our hours is fixed, but if it was pinned, you would have a zero moment at the supports and a very big sagging moment at the midspan, and that results to the failure of your rafter or your beam through deflection or bending. And to resolve that, you are compelled to use a section size which is much more deeper. And so when you increase the depth of the section, automatically the cost will go up because the deeper the section, the higher the cost. And so you need more money for the fabrication, for the processing or the manufacturing of the sections, and also for the erection of these big and heavy steel sections. So it's always good to prioritize on the longer sections and you make them to be fixed at the ends so that you are going to have less deeper sections and you economize your design. Again, you look at the columns, again, they are also fixed. And the reason why our columns are fixed is because of the same reason. When you have your fixed, your columns are, are having fixed end conditions, what happens is that you are able to reduce this factor here called the effective length factor. You know, one of the failures that happens in columns is Euler buckling. And to resolve this, it is important to reduce the effective length factor because as you can see, this is how you calculate the buckling, critical buckling load here. And what happens, we have various end conditions. We have for pinned and pinned or hinged end conditions with an effective length factor of 1. And for the fixed we have 0.5. For the fixed free we have 2, and for the fixed pinned we have 0.7. So we have for the fixed we have 0.5, and this makes that results to this makes the ends, it prevents the ends from rotation. And when you reduce this factor, you make the buckling resistance of the section to be high. Why? Because when you reduce the factor K here, what is going to happen is that the critical buckling is going to be high, and that results to a higher buckling resistance. You can see this. And that's also important when it comes to reducing the lateral rotational buckling. So that's why it's important to make your columns to be fixed when it comes to portal frame structures. Another thing I would like to mention is that it is also important to do this because when you do section optimization, just like I've explained, you are likely to have a structure which have a good structural integrity, and at the same time you minimize the cost, the cost and also the quantity of steel that you are using. Remember that steel manufacturing is one of the biggest causes of carbon emissions, and today we are talking about green construction. And what that means, in as much as we are trying to minimize or to regulate or to change the manufacturing processes for the steel by using green manufacturing, it's also good to consider our designs as engineers, because if we can solve this from design, it is going to be easier to minimize the carbon footprint that is emitted to the atmosphere and that is resulting to global warming. So I want to draw your attention to something important here. You just come here to report, and then you come here to what we call the material listing here. And you just come here and you check what we call the material listings like this, and then you go to show report, and then you can see this in Word. We are going to see this in Word. Let's just export it and we see it so that you can see it well. So just come here. So you can see here we have the section sizes, their length and mass, and we have these embodied carbon emissions. The good thing with Tekla Structural Designer is that you can see all this, and this is important because today we are talking about green manufacturing. So you can see that the bigger the section, the higher the embodied carbon mass. So it is important for you to consider the aspect of section optimization, because if you are to use, if you can minimize the quantity of steel that you are using and still you have a stable structure that is able to withstand the loading and be that is robust against collapsing, still by still using smaller sections or economical sections, what is going to happen is that you are going to have less carbon emission, and that is going to go a long way when it comes to uh, the environmental aspect of our design. So you can see here, this section of steel 152 by 152 has a length of 54 meters, and you can see it has an embodied carbon mass of 2157 kg. That means for every size of this beam manufactured, we have this amount of embodied carbon mass emitted into the atmosphere. So it's important to consider all this. So let's continue. Now we are going to proceed here to our design. So just come here to structure. Now, after we have done all this, supposing you want to generate your you want to generate your data for the connection, the resistance, the building loads, and all, and the material listings. You can do all that as I've shown you. And if you want the foundation reactions for the design of foundations, you can just come here and you show the report just like I've done. You can just come here so you can see it in one. If you want to see it, you can just come here and you can just check all this, and it's very easy to check this. So you can just see all this. It's very easy to see that. So again, you can just come here, proceed, and if you want to do the drawings for this, maybe for the assembly drawings, you can just come here to draw, and then you come to drawing management, select general arrangement drawings, and you can just go add this, and so just see, you can just come here, just come here to this, you can just add this, to content. Let's just stop at that, because if you want to see all this, you can always proceed with the way you want to do it. So we're going to look at that in our next video, and for now let's just stop at this point, and thank you for watching, and continue subscribing. In our next video, we're going to design the connections for various connections. Here we have the hinge connections, here we have the apex connections, here we have the beam column connections and beam to beam connections, also the base plate connections and all that. We're going to handle that in our next lesson and in our next presentation, and we shall be doing that in Idea Statica. And then after that, we are going to do the generation of assembly drawings, general arrangement drawings, and single part drawings in Tekla structures. Thank you for your time, and continue subscribing to this channel so that you can get to learn more and more. Thank you for your time. I'm out.